And we're recording. Okay. So, like I said, so these two files are up on Isidore. They are to solve the pumpkin problem with the ODE45 function in MATLAB. So it's an example to kind of show you what you're going to need to do on your final project for task 3 and task 4 to integrate your equations of motion or your ordinary differential equations for the roller coaster. So what I did was I wrote this all out for the pumpkin problem. You should be able to kind of take what you had from your Euler solution and make the translation between the two and see kind of what's similar, what's different. So what the purpose of using something like ODE45 is to do the exact same thing we did with the Euler method. So with the Euler method, we were taking the integrals of our ordinary differential equations. So for the pumpkin problem, we had 4 ordinary differential equations, right? We had a dx dt equation, which is equal to the velocity in the x direction. We had a dy dt equation, which is the velocity in the y direction. We had a dvx dt, which is the acceleration in the x direction. And we had a dvy dt, which is the acceleration in the y direction. So these were our 4 differential equations that we had for the pumpkin problem. And if we take the integrals of these 4 equations, we're going to end up with position in the x, position in the y, velocity in the x, velocity in the y. So that's the result of our Euler method. When we applied it, we got those 4 quantities out of the problem. ODE45 does the same exact thing. So you give it some equations, and it integrates those equations, and you get the resulting quantities out of that. So it just replaces the Euler method, and it actually uses a different method to solve the differential equations. It uses a 4th order Runge-Kutta solver, which you might have heard about in your differential equations class. That solver is a more accurate solver than the Euler method, so you're going to get better results out of the ODE45 function. I mean, if you really, really want to write the Euler method for the final project and use that, you're more than welcome to. I guarantee this will be easier because we don't have to write a whole lot of extra code. So what do we have to do to use the ODE45 function? So you have to have something, some MATLAB code that will actually call and run the ODE45 function. That's a built-in function in MATLAB, and that's what this script is. So this ODE45 pumpkin script actually calls and runs the ODE45 function. The other file, the pumpkin derivs, is a function that contains kind of the guts of the stuff that's related to your problem. So at the end of the day, it's going to contain all these ordinary differential equations. So in order to do this and apply this in the final project, you're going to need to write kind of 2 files that resemble this very closely. So the script itself has a couple different parts to it, and I'll kind of skip down to the bottom first and then talk about, or maybe the middle, and then talk about the top. So right here in the middle, we have the actual ODE45 function. That's a MATLAB function, and it gets 3 different inputs. The first input is what's called a function handle, and it's basically just the name of the function that we want to use that's going to have all the information about our problem. And this is a special type of notation in MATLAB. That's called a function handle. It's got that little @ symbol at the front of it, and so you have to put @ and whatever the name of your function is in that space. The @ symbol tells MATLAB, hey, that's a function. Go look for that on your computer somewhere, as opposed to looking for a variable that might be called pumpkin derivs. So that just tells MATLAB to go and look for a file or a function that has that name. So you got to make sure that you have that @ symbol and then the name of your function there. The second input argument is a vector that has 2 values in it that tells MATLAB what time frame you want to integrate your equations of motion over. So the beginning time, the ending time. And then the next input are the initial conditions. And you have to have an initial condition, just like we did with the Euler method, for each one of your equations. So we have to have an initial position in the x and y. We have to have an initial velocity in the x and the y. And that's the initial conditions for our 4 ordinary differential equations. We have to, just like we did with the Euler method, the integration methods have to start with something so that it can move forward in time. So how do we define t-span and then these initial conditions? That's what I have up here at the top. So at the very top of the code, I said t-span starts at 0, ends at some sort of final time, 9 seconds for the pumpkin problem, and then I defined my initial conditions here. So you'd have to do something similar for the final project. So the other thing to talk about is what do we get as results out of this ODE45 function. So the first output that we get is t-out, which is a vector of time values. The first value is going to be the initial time, so 0 seconds. The last value in that vector is going to be the final value that we specified, so 9 seconds. Everywhere in between, we don't have control over that. MATLAB picks how many values go in that vector and what they're going to be. So MATLAB determines kind of how it goes from the beginning time to the end time using when it's integrating your equations of motion, and then you get that back out as a result. It kind of tells you, hey, this is the time vector I used. And then you get this matrix called solution. And in this matrix, you're going to have multiple columns, one for each one of your quantities that are the result of integrating your ordinary differential equations. So in the first column in this problem, we have x, because that's the integral of our first differential equation. Then we have y, then we have vx, then we have vy. So that's what we're going to get in solution. So for the number of differential equations that we give to ODE45, we're going to get that same number of columns back in our solution matrix that we have. The solution matrix lines up with the time vector. So if the time vector has 100 things in it, solution is also going to have 100 rows in it, and that tells you kind of what the time is at each one of those values that's in solution. And then the only other thing I have in this script is just some plots to kind of output the results and visually see what's happening. Let's see. One thing to keep in mind with the ODE45 function is that, like a lot of things in MATLAB, it doesn't care what these numbers are. So it doesn't care, it doesn't know that this is x, and it doesn't know that this is y, and it doesn't know that this is vx or vy. That's our job to keep track of. MATLAB just sees 4 numbers there. And so it's our job to keep track of what order we've put that in, and that defines the order of a lot of things. So if I have the order of my inputs just like this, that defines the order of the columns that come out in the solution. So they're going to be in that same order. That also defines some things over in the pumpkin derivs function. So once we've established that order, we've got to be consistent and keep that order amongst all of our different files that we have. Okay, so what is ODE45 actually doing? It's integrating our equations of motion. So it starts at the initial time. So it starts at time equals 0. We gave it some initial conditions. We gave it initial x, initial y, initial vx, initial vy. And then it says, okay, now I got to get over to the next time step. So I've got to move one time step over and figure out what my 4 quantities are, what my position and my velocity are at the next time step, and then repeat that over and over and over again until I get to my final time. So how is it going to do that? So we give it the initial conditions, and then it's got to figure out how to go from there. So what it does is that every time step, every time it stops, it says, okay, now what do I have to do? It goes into this pumpkin derivs function. So you told it that that's the function. It's going to go over there, and it's going to do some things that are going to help it figure out how to get to the next time step. So this pumpkin derivs function is kind of in this format that's specific to what ODE45 needs to be able to get this information and move over to the next time step. So this function has to kind of follow this same format and be kind of set up in a specific way so that MATLAB knows what you're giving it. And there's a couple things that have to be set up the way that I have them here, and then the rest of it can kind of come up, you can write it however you want. So the things that need to be set up in a very specific way are this first line. So the function line up at the top has to be kind of set up this way. You can call it whatever you want, but the name has to match the name of the file. And then it has to have these 2 inputs. So the first input is time t, which tells you the current time. So the very first time that MATLAB's going to go over here into this function, t is going to be equal to 0 because that's where we're starting. And so that value is just going to be equal to 0. That's it. And then states here is another input, and that's going to be a vector of values. It's going to be a column vector. MATLAB defines it like that, and we can't do anything about it. We just have to deal with it. And it's going to have the same number of values in it that we have as we have differential equations. So because we have 4 differential equations in the pumpkin problem, states is going to have 4 numbers in it. And those 4 numbers correspond to, at that particular time step we're at, what are the values of x, y, vx, and vy right now at this time step. So that's the input to this function. We get the current time, and we get kind of the current states of our system, or the current position and the velocity in the case of the pumpkin problem. And then there's a whole bunch of stuff in the middle that kind of helps us calculate all the things that we need to calculate for our problem. And that's the stuff that's going to change. It's going to be different for, however you write it. That's up to you. It does not need to follow a specific format. The thing that does need to follow a specific format are these last couple lines. So in this function, the first line needs to match what I have. The last couple lines need to match the same format that are here in the pumpkin problem. So in the very end of this function, we need to tell MATLAB what our ordinary differential equations are. So we wrote out, or we had for the pumpkin problem these 4 differential equations. That's what I put down here in these last 4 lines. So ODEs is a vector, also a column vector, and it's going to have the same number of rows in it as we have differential equations. So we have 4 equations, 4 rows, and each one of those equations is exactly kind of what I have up here. So my first equation is the derivative of x with respect to time, which is my velocity, and then all the way down to my last equation, the derivative of the velocity in the y direction with respect to time, which is my acceleration in the y direction. So by doing that, by telling MATLAB what those differential equations are, it can figure out how to go from the first time step to the next time step to the next time step, all the way down to the last value that we have. So that's what pumpkin derivs, or that's what these 2 files do, and that's what ODE 4.5 is going to help us do. So at the end of the day, once we've done all of this, we're going to get the results of our differential equations, the position, and the velocity in both the x and the y direction. So if I go to run this script, so you run the script, MATLAB will find the function and do what it needs to do with the function. So if I run, oops, I stuck a keyboard in here somewhere. Let's see. Get rid of that. So if I run my script and then I get my final plots, these are the results of my integrating my ordinary differential equations. So I get position in the x direction, position in the y direction, velocity in the x direction, velocity in the y direction. So you can see just visually kind of what happened when I integrated those equations of motion over my time span 0 to 9 seconds. So in a nutshell, that's what ODE 4.5 does. Now you have to figure out kind of how you can modify these 2 files to be applied to the final project where we have a different set of ordinary differential equations.